Okay, today we're going to find another way to find whether a series converges or diverges, and it is called the integral test. Basically what the integral test says, if you have a positive, continuous, and decreasing function, so you have a graph where the graph is decreasing, and if it's true that the integral converge, then we can say that the series converges as well. So basically making a connection between the area underneath the curve from 1 to infinity, which is really the same as adding up an infinite number of things. So in order to apply the integral test, what we're going to do is, instead of thinking of it as a series, we're going to rewrite this as an integral. So instead of going from 1 to infinity of sigma, I'm going to write it with the integral symbol. So 1 to infinity, I'm going to replace that n with x squared plus 1 dx. And now this is just an improper integral that we covered in chapter 8. So if you remember, when your bound is infinity, we have to rewrite it with the limit statement, 1 to t of x over x squared plus 1 dx. How do we find this antiderivative? Notice this is your 1 over u du, because your u is x squared plus 1, your du is 2x. So this integral, or the antiderivative, is going to be 1/2 natural log of x squared plus 1. And now I will plug in my bounds. So 1/2 natural log of t squared plus 1 minus 1/2 natural log of 2. Now, if I go ahead and take this limit, if I plug in infinity for t, the natural log of infinity is infinity, so this whole thing I say diverges. So if the integral diverges, we can also say the series itself diverges by the integral test. Okay, the important thing to keep in mind is that the series does not equal the same value as the integral. Because in the integral, we're adding up infinite number of things from 1 to infinity. In a series, we're only doing it for selected values, for when n is an integer, 1, 2, etc. So they're not the same value, but however, we can make the same conclusion about whether they converge or diverge. Okay. Let's try another problem. So let's apply the integral test to 1 over n squared plus 1. Same thing, I'm going to rewrite this with the limit statement. First, 1 to t of 1 over x squared plus 1 dx. So I've done a couple things in one step. Rewrite with the limit statement as well as rewrite it as an integral. Okay, how do I integrate 1 over x squared plus 1? This is going to be your arctangent of x. Let's plug in our bounds. Arctangent of t minus arctangent of 1. And let's go ahead and take this limit. If I plug in infinity for t, the arctangent of infinity is the angle pi half. The arctangent of 1, what is the angle that gives you a tangent value of 1 is pi fourths. So this is pi fourths, so I can say that the integral converges. So I can also say this series converges by the integral test. Again, it does not mean that the value of the series is pi fourths. We can just make the conclusion that it converges. Okay? We are not interested to see what the sum of this series is. Okay, one last example. Okay, so I'm going to do the integral test here as well. Rewrite it as integral. Rewrite it with the limit statement. And how do I take this antiderivative? Your u is ln of x. Your du is 1 over x dx. So that means this antiderivative is really the natural log of x. And I notice as soon as I plug in t, I'm going to end up with the natural log of infinity, which is going to be infinity, so I can say this diverges for sure. So therefore, the series diverges as well by the integral test.